So we keep on building in our skills to get to our next level of answers required that you'll find in the HSC exam. So if I come back up here, like we started with mass by acceleration, force by distance, magnitude and direction, and those all helped us to work out like calculating moments and forces within a beam, usually found in civil structures, but you can actually find this occurring within aeronautics as well. So here we are like with the shear force and bending moment diagrams. Now you can't work this out unless you can actually do this. Okay, so they're working together to be able to get you to the correct answer. Okay. So the shear force diagram represents the sum of shear force reaction at a given point along a beam, and the bending moment represents the sum of the moments acting at a given point along the beam. Okay, so basically we're just having a look at how the material is working, or actually how the beam is working when it comes down to it. So here's our first example. We have our beam, we have a roller, and we have a pin, and we have forces that are coming directly down. Again, quite a simple diagram. If we had these on angles, we'd also then have to rectify that to get horizontal and verticals. But in this case here, they're coming down. Also with the horizontals, there wouldn't be a shear force there because it's moving. Okay, so there's no shear force or bending moment on the horizontal because it's moving, so you don't have to worry about plotting that. What we're looking for are these vertical forces. So the first thing we need to do here, I need to find out what the reaction at B and what the reaction at A is. So I'm going to take my moments around B to be able to find out what A is. Okay, so as we come down, again, I'm not going to spend too much time here because we just did this already. Reactions at A, we're looking at the sum of moments, and reaction at B, we're looking at calculating the forces, like the sum of all forces. Okay, so once we've actually got that done, we can then start looking at drawing our diagrams. And I've come back here and I've gone back to my force diagram to put in what I know. Again, this is me. I'm putting this in as what I actually know. You're going to find in the HSC paper, they're going to give you a diagram set out like this with these lines already in place. And they expect you to use them as such. Okay, so that's why I've set this up here. You can see it mimics the drawing up the top here. So 2 meters and 40, 6 meters and 90. And that's what I've done here, 2, 40, 6, 90. And then I've got put my other resultants in. Now, the way that this shear force diagram is actually drawn, we are actually following the forces that are here, that are actually in this first diagram. I've got to try and stop saying actually so much. But these forces here, we are plotting the points. So for equilibrium, we know that we've got a straight beam, and the beam will be at 0 at both ends to know that it's actually steady and not falling down. Here, my first point is 50 kilonewtons. So my plot, as I point them, I've come up 50. Straight up 50. So that is representing where the roller is on the original diagram. You can see here now the distance comes in 2 meters, and then we've got a force coming down of 40. So straight line across, no worries, just bring that straight across. Right. If it was a universally distributed load though, which basically means that the weight is the same, it would actually be a diagonal, and I'll talk about that in a second. Let's get back to this. Up 50, across 2. Now I've got to come down 40. So 50 less 40 is 10. Okay, so I'm coming down 10. I've now got to traverse 6 meters, or come across here, 6 meters, and now I'm coming down 90. So 10 less 90 equals minus 80. Okay, so you can just see I'm subtracting 50 less 40, 10 less 90, and I've come down to minus 80, and you can see here I've got 80 newtons coming back up, so minus 80 plus 80 brings me back to 0. As I said, nice and easy diagram, plotting the different points. starting and ending at the 0. Okay, it's a nice little way of checking your actual math as well. Now, the easiest way to do the bending moment diagram, I'm just going to have to, am I going to fit? Sort of do. Okay, I'll come back to it. So to calculate out this bending moment diagram, the easiest way to do it is by working out the area that we've actually got within the shear force. So here, if you can imagine that this is, it's almost a square, you could say, right? What is the area of this space? I've got 50, I've got 50 coming up and I've got 2 coming across, 2 meters, right? So that's 100 in the area. Coming down here, that's my first point. And again, you can see it's continuing down on this line. First point is 100. Okay, let's have a look at the next area. I've come up 10 and I've gone across 6. So that is going to be 60 across here. However, with this next point, it's traversing the whole diagram. So I can't forget about what I've done here. So what have I got? I've got 100 plus my 60, which gives me my second point at 160. Again, to make sure that I've got this right, I've come down 80 and I've got 2. So minus 80 by 2 is minus 160, which brings us back down to our 0 point. Okay, so that's what we're doing there. We're plotting this, and that's the easiest way to do it. Sure, you can go back and do it analytically, but this is going to be the way to do it, and it's going to save you a whole lot of time in the actual exam. Now, like I mentioned before, one of the differences that we could actually have is when we've got a universally distributed load. So imagine that this beam has a weight, there's no truck on it or anything like that, it's just the weight of this beam. All right? And we know that for every meter it says here, it's 30 kilonewtons. And it goes for 20 metres. Here they've done the math for us as well, and it's quite, you can understand if it's universally distributed load, then it should be the same forces at the pin and the roller. So here I've got 20 metres, 20 by 30 is 20 by 30, my math is out today. Yep, 20 by 30 is 600, and that'll leave us 300. My God, I'm failing on that math. Oh my goodness, I'm in trouble. 30 by 20 is 600, which means we've got 300 kilonewtons at each end of the beam, holding it up, okay? Now, again, you may see this universally distributed load drawn in a couple of ways. It could be arrows that are straight down, right? Or the other way that we have seen as well are these little arches. Don't get confused, they mean the same thing. It's basically saying it's a universally distributed load. Now with this, because it's actually universally distributed, we know that we're going up 300 and we're going to come down 300, and then this point will cross in the middle. Okay, so for a universally distributed load, it then forms this straight line for us. Okay, a straight line like this. Okay. So again, you can plot the points up 300, down 300, and there we go. It's a straight line right through the middle. Again, if you wanted to, if you don't believe me and you don't trust me, you can then calculate the first moment, and then you can calculate the second moment, then the third moment, and you can plot each of those points along the way if you wanted to actually test it out. But generally speaking, it's a straight line between the two different forces at the pins. Now, coming back up here, to calculate this, we did the area of these sections, okay? Now, in a universally distributed load, our formation here is a triangle. So we need to actually calculate the area of this triangle to find this point here. So the area of a triangle is half base times height, right? And in this case here, we've got half multiplied by 10, which is this distance here, that's 10, by height, 300, which then turns into, it turns into 1500 kilonewtons, or 1500 newtons. That's why we've done that there. Should have had an N there, 1500 newtons. Okay, so again, these aren't difficult. It's a matter of knowing the process in how to plot it. Basically just plotting the forces as we come across them. Universally distributed load, it's a straight line, and what we're doing, we're calculating the area within the shear force diagram to find the points on our bending moment diagram.